Okay. Yes, you're welcome, everyone. So today, let me just close this up. All right, today we'll be just going through Foundry in detail. Yeah, today we'll be just going through Foundry in detail, looking at some of the things we didn't cover yesterday, and yeah, seeing a little bit more detail in terms of smart contracts testing and exploring Foundry in detail generally.
And
So
yeah, seeing a little bit more detail in terms of exploring
just a
Foundry in
moment.
detail generally. So just a moment.
All right, so I'll just look for the file we opened yesterday. That's exactly what we'll be using.
All right, so I'll just look for the file we opened
I
yesterday.
think it was called,
That's
I
exactly
don't
what
remember
we'll
the
be
name
using.
myself. I'm sure we can find it.
I think it was called,
It was,
I don't remember the name myself. I'm sure we can find it.
Foundry tests, yes.
It was,
It was Foundry tests. So with Foundry tests, yeah, everything was in here, the files.
Foundry
And,
tests, yes. It was Foundry tests.
the Foundry
So with Foundry
application
tests,
we
yeah,
created,
everything was in here, the files and
Foundry project.
the Foundry
Just a
application we
moment.
created.
Yeah, I think this is the application we created yesterday, rather the smart contract. We didn't actually create it, we simply made a few changes to the default smart contract in Foundry. And so today what I will do, I think I will actually entirely replace it, and create something new. So we'll be writing a few tests and scripts, yeah, just to, practice this whole thing of writing smart contracts, testing smart contracts, and hopefully we can get some time and go through a bit of advanced concepts to understand deeply how the EVM works and how Foundry exposes some of these features through the edge cases that it enables as some kind of Solidity DSL. So yes, from yesterday, you remember, we had this specific file, and all we were doing is simply setting a number and then incrementing the number, and then we did a few tests. Yeah, we looked at things like start prank. We looked at vm.deal. Did we look at deal? I think we did vm.deal, make address, and all those other functions that would enable us to interact with smart contracts in a framework that allows us to test them. So today we'll be creating something entirely new, and hopefully the session is short and not very technical. So I'm going to just create a new file from each of these three folders, the three most important folders, which is of course the test folder, the SRC folder, and the script folder. And like we talked about it yesterday. We use these three folders for very different things. Scripts is using for writing scripts, just like you'd write scripts in your terminal. So you'd simply shift them into this folder, and there would be scripts that probably interact with your smart contract. And then if you want to test your smart contract, you can put your smart contract in the test contract in the test folder. So I want us to write a simple smart contract that basically Yeah, maybe someone could suggest a smart contract we could write, and then because the focus is really on the tests and scripts, but the smart contract could be anything. So I want to write a simple smart contract that has concepts of access control and perhaps also concepts of yeah, maybe we'll start with access control. Would have maybe one function that is restricted to the user, rather to the deployer, and then the other functions are simply, accessible to everyone else. Okay, so inside the SRC folder, of course, I'll create just a single smart contract here. I'll call it let me give it a random name, incrementer.so, and then I'll start writing my smart contract. Of course, these are preliminaries. You need to specify the compiler version that you're going to be using. I prefer to use a version that is slightly backward compatible. Okay. And yeah, so that's it. Then I need to specify under what license I'm writing this smart contract. It's really just the boilerplate, only that I'm writing it myself. I could say this is unlicensed. So that gives rights to anyone to reuse it under their own discretion. Yeah, let me call this contract incrementer. Maybe increment. And I'm going to give it a simple definition from here and say perhaps I don't know why the library keeps opening. I don't need this, I don't need that, I don't need that. So I'm going to give it a simple definition and say this contract represents a simple protocol where a user can increment number but only the admin can reduce the number. Maybe I could write a simple safe. What do you think? Actually, yeah, let me write a safe. This is an on-chain safe. Something that is short and simple, so I'm going to call it bank. Let me change this name to something a little bit more appropriate and call it on-chain safe. All right, so I'm going to write a simple safe, and it's a number of basic things. So I'm just going to write one in a very fast-paced kind of way. I'm going to say safe balance here. So now I'm defining the state variables in a very simple way. U into 56, safe balance, and probably this is public. And then I want to have a mapping, public mapping of savers, so that stores the address of the saver, then the value they have saved. And maybe another array of the saver's addresses so that I can loop through them and be able to, access the values that they've saved. And let me say it's just an array of addresses, a dynamic array of addresses, so I'll call it savers addresses. I'll still make it public. Okay, so I'm just going to put two simple functions, one for deposit and two functions for withdraw, one for the one for deposit, another for withdraw, and another for, withdraw from the contract by the deployer. So what I'm going to do here, I'm going to define a function deposit. I don't even need to, this has to be external and payable because it has to receive funds, So I'm just going to maybe also emit a few events. Deposit. Deposit success, then I'll simply print the address of the person that has deposited and the value they've deposited. Unit 56, and I'll just call this value. So here, simply what I want to check for is that there's at least a balance, rather there's at least some value that has been sent when this contract has been called. So I'm going to say if msg.value should be greater than 0. If not, you should give the revert statement here and say the value is not greater than 0. Okay, so that's the only condition I want to put across. So when I'm done with that, then I'll pass the address of the caller to the saver's addresses as an entry, and also the value that I've deposited. So I'll put that under mapping, saying save. I'll say savers. So on the mapping, I would simply do exactly the same thing. Sender, then equate this to the amount that I've stored. Okay, that's all I wanted to do in this function. And then I would emit the event. Say deposit success. The very first argument is an address. Depositor, I want this also to be indexed. I'll explain this later when we're looking at the tests themselves. So deposited, if I was depositing, the address would be msg.sender, and the value would be msg.value. Okay, so that's function 1. Then function withdraw, really simple as well. It's also going to be external. Since I'm not really it's going to be external. Since I don't really need to call it inside here, I would say withdraw success, still the address. I could actually simply copy this and change the name because it's essentially the same thing that I'll be doing, just that I'll change the name. Withdraw success. So now I have two events. I'll be emitting one in the deposit function, the other in the withdraw function. So withdraw external, and then I'll initiate the withdraw. So the person wanted to withdraw, maybe they specified an amount they want to withdraw, 256, and I would enter the amount. But first of all, I would have to check. I'm going to get the value that they have in balance, first of all, to see if they actually qualify to withdraw the amount they want to withdraw. So the amount they have in balance, I would call this on the savers mapping just to find out the value they have. So this would return the value, which would be a U into56, msg.sender. Then I require to see if balance is greater than the amount. If the balance they have, the credit they have on their account in this contract is greater than the amount. I would say balance insufficient, funds insufficient. Okay, that's all. And then if they do have that amount, then we can proceed to send them the funds. So I would have to make their address payable. So this is how I would do it. First of all, I would want to get the result of the operation, the Boolean result. Either it was successful as an operation. So I'll have to make their address payable, msg.sender, and then I'm going to send them these funds using a low-level call. So in here I would have to put the value that I'll be sending, so which of course equates to the amount they want, and yeah. So that's the function, and they will be able to receive the funds. So since I'm not calling any function along with this, since this is not another contract I am sending funds to, this field would be empty because it represents the call data. If I was sending these funds to a call, rather to one external contract through a delegate call or just a low-level call, I would have to put call data here, but maybe that's something we'll look at later. Okay, so this line of code would send funds to that address and then would return a Boolean result of whether the transaction was successful or not. And if it was a call to a contract, it would return a bytes array of the result of the call, of the result of the transaction or the call that I sent to the other contract. Okay, but since we are not sending a call to a contract, we can leave the second parameter empty. And then here we simply check if the transaction was successful. Otherwise, would say failure to send and simply revert the entire state back. So after we've confirmed that the funds have been sent, would then have to reduce the amount that this person has here, minus equals. This would subtract the value that will be returned from this statement from the value that I'm going to put here next, so from the amount. So it would subtract the balance they had from the amount they've withdrawn, then they'll get the new balance. And then after that, we can emit the event. The event, say, withdraw success. Their address, of course, would be msg.sender. And then the value that they've withdrawn, in this case, it's amount. Okay, so those are two functions. Now the third function is the one that is going to be it's going to be for the what? For the deployer of the contracts. So maybe this specific contract has rights to withdraw funds and use them for something, then can return them to the contract, or they could reduce the funds that have been deposited by a certain percentage as a way of charging fees for using this platform as a savings platform. So I'll call it a deployer withdraw. I'm just going to keep it simple. They could also specify the amount they want to withdraw. I could actually do exactly the same thing, but let me redo it here. U into 56, and they would specify the amount they want to withdraw. And it's of course also external payable, rather it's not payable because it's just a withdraw function. Let me also emit another event here saying event here saying deployer withdraw. So this is the utility of events. This is something you wouldn't otherwise have capacity to do in Web 2. Kind of listening for events or operations that are being done by a restricted function. This you wouldn't do in Web 2. For instance, if you had funds in your bank account, there's no way you could tell if your funds are going in a certain direction and what they're being used for. But with events, we can track the utility, rather the log of a smart contract. No matter what function is being called, if you're tracking the function, the contract log, you can get all the emissions, all the events that have been emitted from that contract, regardless of whether you have access to the functions from which they've been emitted or you don't. Because you're simply reading data from the blockchain, so you have access to everything that is made available through the log and through state variables being public or external. Okay, so the deployer can specify the amount. So the deployer, of course, is not restricted. They can take out any amount they want. So all we need to do is do this. Send them the money. Don't ask them questions. Simply send them the money. Or perhaps the only thing we could check for if the contract actually has that balance. So we would simply say check the balance of this address. They may ask for a lot more than what is existent in the contract at that time, so we want to check the balance. If the balance is greater than or equal to, let it be greater than or equal to the amount that I've specified, then the transaction can proceed. Otherwise, it's say insufficient funds. Insufficient funds, okay? So we are almost done with our smart contracts. Smart contract, very simple smart contract. So if the balance is within the range of their request, then you send them the funds. But now this function has to be restricted because it's supposed to be called by only the deployer. Otherwise, everyone would be able to withdraw funds from this smart contract, which is not very ideal. It's very insecure. So this was a deployer withdraw and the amount that they withdrew. So I'd simply put amount here, and yeah. So that's it. That should be it. Then I emit the event that they've actually made a withdrawal. And so now I want to use a very specific access control feature called a modifier. Actually, how modifiers work is, I'm going to call it a deployer. So up here, I want to specify the address of the deployer. Address of the deployer, and I want it to be immutable. So there are two very specific keywords that allow you to write state variables directly into the bytecode of the contract without you having to use the storage slots of the EVM. Two of those words, one of them is immutable, the other is a constant. So when you declare a state variable as a constant, it will never be a part of the EVM slot variables. It is embedded directly into the bytecode. It's kind of like a precompile. We shall look at precompiles maybe. And the other word is immutable. So immutable state variables are the ones you declare, and then rather you initialize. Yes, declare, then you initialize them when you are deploying the contract. That means inside the constructor. Beyond that, there is no way you can change them. But constants are generally just constant values. You can only assign them at the point of their declaration. So if I wanted to declare a variable as a state variable as an address and I want it to be constant, I have on this very line where I am declaring that variable is where I have to initialize it. I don't have access to this state variable elsewhere in the code because it's designed to be constant. It's not supposed to change, in other words. So yes, the deployer would be there, then the modifier function. So the modifier function, inside the modifier function, I'll simply put a require statement. Require statement. And request to find out if the smart contract, rather the either the smart contract or the externally owned account that is invoking the specific function where I'm going to put this deployer modifier is exactly the same address like I had designated as the deployer. So if it's not, you'd say unauthorized access, unauthorized, that's enough. Then after here, you put an underscore and then a curly brackets, is a colon. So this is how modifiers work. I hope I could demonstrate it with Paint. So a modifier is like a wrapper. So if I have a function, for instance, if I have a function and I put a modifier on it, now the code that is inside the modifier, every code that is around, either before or after, around that underscore and the colon, this underscore and colon represent the function body. Every other line of code that is inside this function body will be represented by that underscore. Now that means the code that is coming before and after the underscore and the colon will execute in that order. The code that comes before will execute before the code inside the function. Will execute before the code that is represented by the underscore, which is the function body, everything inside there. So that means that this line of code would represent the code that would execute at this point, and this line would represent the code that would execute at that point. So that means everything inside the function would execute in between these two lines. Whatever I type before the underscore would execute before the function body. So it's like you're wrapping the function inside a set of inside some kind of function itself. So this code would execute, and this is where you would put your access control statements. Like if the specific parameters of the call context do not meet the standard that is required for the caller to call this specific part of the contract, which is of course the function, then the transaction would revert at this point. If they meet the requirement, then it would go on and execute the function code base, and then if there's any other code after that, it would execute it as well. So that's what the modifier does. It kind of sandwiches the function, and everything that is put before the underscore in the modifier executes before the function. So every time you put something, so this would be like the modifier, then this underscore here, for instance, if I was putting this modifier on the deposit function, all this code would be executing within this context of the underscore, right after the require statement. So that's how modifiers work. They kind of sandwich the function. And for you to give a function a modifier, you simply put it after the state, the visibility modifiers, things like external, internal. I'm sure we looked at that. So I'll simply put it here, and before the return statement, if this function was returning anything at all, the deployer, all the modifiers have to come before the return function, the return statement, but before the visibility modifiers, before the state mutability modifiers, things like pure and view and payable. Okay, so that's it. I think that's essentially our smart contract. It's called bank, has 3 functions. It's a really, really simple function, rather smart contract. And has a number of state variables, has 4 state variables. Yeah, very simple smart contract. So now we are going to write a script that would deploy this, and maybe we can use Anvil for us to run tests much faster. So we're going to deploy this on the Anvil chain. And let me open this in a new window. So I'll start my Anvil chain here. So if you remember from yesterday, we were talking about Anvil and saying to start an Anvil chain, you simply type the keyword Anvil and it will spin up the chain for you. So that's the chain ID, that's the base fee. If you're going to run transactions on this chain, this is the gas limit. That's the Genesis timestamp, which is the time in a Unix epoch. And this might actually be a few minutes from now. We can verify what time this is. if we convert this into standard time, I want to demonstrate it so we could see it. Unix epoch converter. So I'll simply get this timestamp and put it into, when I put it right here, it would give me the time. It shows Thursday 19th, 2026. Is today Thursday? It is Thursday, yes. And 2:51:37 p.m. This is GMT or UTC time. And my time, which is GMT plus 3, is exactly 5:51, and you can see it's just only us slightly behind by a few seconds, but so that's the time, okay? And that's the time we exactly spinned up our blockchain from here. If you could see that again. And yeah, it is listening at this post. So that is like the RPC URL, the RPC of this chain, the Anvil chain. And so I want us to now deploy this smart contract on that chain using the script. So we're going to write a simple script for deploying this smart contract. So we have the smart contract, and for us to interact with, to create a script file to deploy it, first of all, we have to, of course, create a script. So I'll call it on-chain safe. So there's a convention where script files are recognized, are defined. Let me first type this, on-chain safe, where script files are defined with a .s before the extension, because everything inside Foundry is a Solidity file. The only changes come in when you are writing tests or scripts where you extend certain interfaces and specific contracts that enable you to interact with Foundry specific components of Solidity. Okay, so this is a script file. I'm calling it onchainsafe.s.so. And if you're going to write a test file, it would be onchainsafe.t.so perhaps. But it's not a requirement, it's just a convention for making it easy for you to, explore your file architecture, your file setup, and find it easier, to work with your files. And yeah, so here we go. And just like every other Solidity file, it needs to have these preliminaries, the license, and then the Solidity compiler version that is going to be used to compile this code. So I would call it a very simple name. I would say on-chain. And for it to qualify to be a script file, it has to extend the script. It has to inherit from the script file from the Foundry standard library. So I would say on-chain is a script. Now, script is an abstract function, an abstract contract, and we import it from the Foundry standard library as a script from Foundry standard library, which is for std. You don't have to cram the name. The name would always be here in the library. So inside the standard library, inside the library folder, which always contains your dependencies, forge std, then you would find the script file here, script.so. Now this is the file that would have the script contract, the abstract contract. We can try to find it and see if it actually exists inside this library, the standard library of Foundry. Scripts, no, src, it should be here. Script, it's right here. So you might be wondering why I didn't actually type the keyword src. So by default, Foundry would simply resolve into the src folder and look for this file inside the src folder first. Okay, now for a standard script file, there's a function you're supposed to implement which is responsible for deploying these contracts when you write them. And it's the run function. So this could be public. Now inside here is where you start to now write the code for deploying the contracts. But for you to deploy a contract, you must have its contract code, because that's how you would compile it into the contract code that will later be deployed. So I would have to import my contract here so that I can compile it from within the script file, and specifically the script contract. And where is my file? The file is inside src. What is its name? It is called bank. That's the contract rather that I'm going to be deploying. It's called bank. And I'm importing it from where? So for me to reach src, I would have to get into the parent folder where both src and script are. Then from there, then I can get into the src folder. And inside there, I'll be able to find on-chain safe. On-chain safe.so. So that's where I would find the bank contract. Okay, so inside this script file, script contract rather, when you're going to deploy a contract, there's a number of ways you can deploy it, but the one that we typically use in script files is using the new keyword. So I would have to type the keyword new, then the contract name, bank. So conventionally, this would be best if we give it an uppercase, so that then the lowercase would represent the deployed instance of the contract. So new bank, you call it like you would, if you remember constructors. So it's as if you were creating an object instance from a constructor, yes. But now I need to have access to the instance that I'm going to deploy, so that maybe I could use it later on, if I want to anyway. But you see, let's try this and see if it works. So if you remember from yesterday, what we were doing essentially was, I want to interact with it, but I'm trying to find a CLI interface I should use. So yes, I have access to Anvil now. Anvil is running in one of the terminals, as you could see. And by default, if you don't specify an RPC URL for every interaction with a blockchain, Foundry will resolve to Anvil. So if you remember yesterday, we had we imported wallets, and we could check the list of wallets that we have using the command cast wallet list. So it gives me a list of all the wallets that I have imported. But if you remember, I specifically imported Anvil 2 and Anvil 1. The rest of these, even MetaMask, I believe. But I'll work with Anvil 1. And if you remember how we actually import a wallet, it is straightforward. You would have to use the keyword cast wallet import, then the name of the wallet. I would say name. And then you specify if you want to enter the private key, which I said might be a little bit insecure, because then it would expose your secret, the private key. And then when you enter it, you give a password to the key store, or alternatively, you could use the keyword interactive, where you simply enter the private key and paste it, but it's not visible even within the terminal itself. Then you enter a password still to the key store and save it. Then later on, if you want to use the account, the private key particularly, you simply enter the password to the key store and you'd have the results. I went through it yesterday, that's why I'm not going to demonstrate it. Okay, so now we have, we're going to be using Anvil 1 as the wallet. So if you remember from yesterday, when you're deploying with a script, you use the keyword forge first. Then you use the keyword script to specify that you're actually going to be calling a script. Excuse me. Then you start to find the script inside your file setup of your project. So inside scripts, I have this file called onchainsafe.s.so. onchainsafe.s.so. So if my file on chain-safe.s.so had more than one contract, I would use the colon here. I think it's called the full colon. Then type the contract name, the specific contract name that I want to interact with, the specific script contract name. So in this case, this is called on chain. But since it's just one, I don't even need to use this extension to specify. So I could do it like that, or say target contract, just as with the initials TC, then the contract name that I want to interact with. But I'll leave it blank since we have only one contract. So it will resolve to that simple contract, that single contract that exists. On chain safe.s.so. So what do I need to deploy a contract? I need to fund the transaction and then specify the RPC of the chain on which I'm going to deploy. So I'm going to specify the account, Anvil 1. I think it's called Anvil 1. But I could enter the RPC URL. For Anvil, it is HTTP 127. You don't have to cram this, you can find it here still. I'll just copy it. But even if I didn't put it here, it would resolve to Anvil. Okay, so that's it. When I run this, RPC URL, unexpected argument R, where? Okay, I missed out. It's supposed to be a double slash. So it compiled two contracts and failed. There's an error somewhere. Expected a comma, but got that in the contract itself on line 16. Acquire.msg.sender unauthorized is equal to the deployer. I don't see an error, but if you see an error, you could please type in the comments. Let me know where it is. I don't seem to see it. Compiler failed. Line 16 is where I wrote the modifier. Oh, sorry. It's actually a function itself. The modifier is a function. So I think that was the error. So when it compiles and gives me all these warnings. Identifier already declared. The previous declaration is here. Deployer withdraw. Oh, the event. So this is the thing with Solidity. The names don't exactly have to represent the same object type for them to be a collision. You just can't use the same name for any object, for more than one object in the entire contract. So that's the error I was having here. Even if one of the objects was an event and the other was a function, you still get errors. Deployer withdraw. So the issue was the event and the function had exactly the same name. Okay, unit. It's supposed to be a uint. I think I went too fast. Which line is that? Line 9. This is a uint. This is a mistake I make very often. I don't know why I do that. Wow. And it's appearing more than once. 31. I hope I don't end up changing the entire code base. Let me look for it before I uint. I think elsewhere everything was okay. Okay. So yeah, it was successful, but that's just the compilation. Okay, it didn't deploy. Why didn't it deploy? We can find out. There's a number of reasons. So the compilation was successful from here, and the warning says detected artifacts built from source files that no longer exist. Run forge clean to make sure builds are in sync with project files. Blah blah blah. Okay. Um, the script ran successfully, as you can see, but it just ran a dry run. A dry run is simply that operation that demonstrates how things would normally go if you were working with them in live mode. So it's kind of like the sandboxed alternative to what you would otherwise do or what you intend to do. And the sandbox equivalent. So yes, we have this contract and we have the script, and the script didn't deploy the contract to Anvil, even after us providing everything we were supposed to provide, except we didn't really provide everything. So for you to deploy to a blockchain, you need to use the keyword broadcast. What that does is that it broadcasts the contract deployment code signed onto the blockchain, and then the nodes would pick it up and then validate it and add it into the contract, into the blockchain itself. So when I click broadcast, add broadcast there, I expect it to deploy. Let's see if it actually deploys. It still does not deploy. It says no transactions to deploy. So typically what happens when you're writing a script, everything is going to be in the sandbox until you choose to work with a live blockchain. So there are specific commands you type. So when I say new bank here, it's going to create the contract, yes, but it's going to be like creating a contract that I can only use within my script, but not really deploying it on the blockchain. So if I want to work with a live blockchain, I need to specify that specific section that I want to be deployed on a blockchain or to interact with a blockchain. It could be deploying a contract, it could be interacting with a contract that has already been deployed. I could also do that within the script. But since we're going to be deploying, there's a specific set of keywords that we use when we're going to deploy a contract to a live blockchain. And that statement or that function is on the VM interface, and it's called start broadcast. So when you use that keyword, when you call that function start broadcast on the interface, of course the interface is given a contract address, a default contract address, so it's not really just an interface, it's actually a contract instance. So when I call start broadcast, everything under start broadcast will be interacting directly with the blockchain. Let's see if it actually works. So it compiles, and now it asks me to enter the key store password. Because now it's going to deploy on the blockchain, it needs to sign the transaction. Originally, it didn't even ask for the password because it wasn't going to be working with a blockchain. Everything was simply going to stay within the script. Well, let's see what happens now. When I enter the password, you don't see the password, of course. That's the security of it. It now deploys and even gives me the hash and the contract address. So I have deployed on Anvil. When I go to Anvil, Anvil has its own, let me say, miniature explorer here. You could see all the transactions that you've done, and you could see that a contract was created that ends with AA3. When I check here, my contract does end with AA3. So when was this contract deployed? 15:10. That's 3 hours behind me, so that makes it 5:10, or the 6:10. And you can see it's exactly 6:10 my time right now. Okay, so that's almost like it's a blockchain, of course. It's just that it's running locally on your chain, on your machine, but it works exactly like Sepolia would work and any other blockchain would work. So you could see that we've actually deployed the contract with the keyword start broadcast. Now the issue with what we just did is that now everything under here, if this function was doing some other operations, they would all be interacting directly with the blockchain that we deployed on. So whatever we're doing here would be a live transaction, and that would spend gas. So if we were deploying on mainnet, everything that happens after this statement would simply be interacting with the blockchain and then, spending our gas. But you can stop the live operations with a slightly similar function, which just stops the broadcast. Now everything else that comes after it would be now back to the sandbox environment of the script that you're working with. So whatever you wanted to test with the live blockchain would have stopped. For instance, if you wanted to get some values from the blockchain and then do some computations within the script and probably also send a transaction back to the chain, you would do this and it would help you, save a lot of gas. So many applications actually use Foundry in the background as a dependency for them to be able to save gas. So they would only start a broadcast if they want to get something from the chain and then stop the broadcast and do the operations with the results they've obtained in an off-chain environment, and then send it back to the blockchain if they had any values they want to send back to the blockchain. One of the platforms that uses these features a lot is the Chainlink protocols actually. So that's how they are able to be gas efficient and yet still effective in the way that we utilize them as oracles. Yeah, okay, so start and stop broadcast, those are two very important things you need to learn if you're going to be working with Foundry. So they're just a function, two functions essentially. The first one starts a broadcast, so you interact with the live blockchain, everything under start broadcast. Then stop broadcast simply does the opposite. It stops the broadcast and then returns the operations back to the sandbox, the script sandbox. Okay, so we deployed our contract successfully using a script. And we could even see the transaction information here. Only that it's not arranged as you would typically see it on an Explorer. We could actually deploy this on Sepolia as well. I think I have some funds on one of my wallets called Approve. You can deploy it on Sepolia and see what it would look like. I don't have a browser here. Wow. Okay, I'm going to get the RPC URL of Sepolia, then deploy on Sepolia using funds from one of my accounts. I hope this is actually a real RPC. So I'm going to just store it in my terminal here as a local variable, Sepolia. So I can verify if the local variable actually stored the value. Sepolia, yeah, it's actually there. So now I'm going to do exactly the same thing I did previously, only that I'm going to change the RPC URL. And now I will be deploying on Sepolia by just changing the RPC URL. Everything else really stays the same. So when I enter, it is supposed to ask me to enter the password and then deploy on Sepolia, because that's the RPC URL I've specified for this deployment. But let's see what happens. There's something I want us to observe, something very specific. Okay, I don't know if that was an actual URL. I copied a random URL that should represent Ethereum Sepolia. I hope it wasn't. Didn't have issues. Oh, I think it did have a problem. Okay, let me get another URL, RPC, from a credible source. Okay, wow. I will take this one. Okay, I'll simply replace the state variable, rather the local variable, with a new RPC. No. All right, yeah, that should be good enough. And you see it's compiling and then asks me for what? Oh, it's sending me a warning and then ask for the password. So when I enter the password, let's see if it actually deploys. It's attempting to deploy. So it even shows you the chain ID of the chain that you're going to be deploying on, then the gas that you might have used, the estimated gas that you would be using to do the transaction, but then the transaction failed. And it says, I don't have funds. It says there's insufficient funds on this account. So yes, Anvil doesn't exactly have funds on Sepolia. I can verify that by checking the balance on my Anvil One wallet. Cast balance. So I'm just going to write this first because, so ideally that would be this what I'm going to type in here would generate the address that I'll be checking the balance from on that specific chain whose RPC I am entering here, which is Sepolia. So I would have to get a cast wallet, the address, then I derive it from the private key, but the private key has to also be fetched from somewhere. I need to decrypt a key store, and the key store name is Anvil 1. Then I need to truncate the result so that I get only the private key. Okay. We think this is just something you would do if you wanted to get the address. So an address has 64 bytes. Yeah, 1 2 3 4. Oh, says the RPC URL was not supplied. I supplied the RPC, or I typed the name wrongly. And it should show me that, oh, I have very little funds. I do have some funds, but this is very, very little money because it's always denominated in Wei. You could see how much that is with a calculator. Wei to Ether. This must be very, very little funds that I couldn't even cover the gas. As you can see, it is less than a cent. Really, really little. Less than a cent. Because it should display the value that it is in dollars worth of ETH on mainnet, the standard price, which is slightly over $2,000. But you can see there's almost nothing on the wallet. So I have to use a wallet that actually has some funds. So I could check the balance of one of the wallets that I actually think might have some funds to deploy on Sepolia. I think that key store is called Approve. I am sure it has some funds. And yeah, you could see the value is much bigger. So this account I think would help us deploy this contract on Sepolia. This is, yeah, $126 worth of ETH. I wish it was real. Okay, so I'm going to deploy this contract now using that wallet. I'm simply going to change the account to Approve. So it should now be able to compile and then, deploy this contract for me. Let's give it a moment. 1, 2, 3, 4. Okay, so it's setting up, and you can see we are deploying on Ethereum Sepolia. That's the chain ID of Ethereum Sepolia. Then every other metadata about the transaction, the gas, and it deployed successfully. You could see the hash here. We could even verify that. And let me check it on Etherscan and see a successful deployment. Oh, This should be mainnet perhaps. Yeah, it's on mainnet. Okay. So it says it was successful. We created a contract at this address. If we want, you could even verify the contract, but I'm not going to verify it now because I want to do something else. But you could see we successfully deployed a contract using Foundry and specifically using a Foundry script. Yeah, so now that we've deployed a contract, we know what it does. It is a safe, it's just a simple safe. But that safe could be vulnerable to a number of attacks. And sometimes the logic, especially if the contract grows big in terms of the code base, it becomes very difficult to simply look at the code base and see the errors. If you noticed, I was just deploying the contract, but there were errors I couldn't even see when I was writing the contract. Now, there's those, very basic syntactical errors that you might correct because the compiler would even, or the debugger would even remind you before the contract deployment executes that there are actual errors in the contract. But then there are errors that might not be exactly errors in the sense that they would stop the compilation from happening, but there are errors in the logic. There are errors that could expose the contract to, malicious attackers. And those are things that we need to test with Foundry tests, or because this is the standard tool that actually protocols use to test their contracts before they deploy them on main networks for production or for them to go live and be deployed as protocols that we use. And that's why we have Foundry tests. So we have used a script to deploy a contract. Now we need to test the contracts. So we can test for a number of things. So for instance, when I look at this contract, there's so many things that I could test for. I could test for access control. I could test for just how it behaves in different scenarios, even things I might not have already noticed by simply writing this code base. Some of them could really come up when I'm testing the contract. So, of course, to test a contract, you need to write a test contract. So I'll simply call it on-chain safe.t.so. So it's just a convention. You don't exactly have to use it, but for making it easier for other people to work with your code, or even yourself later on when you come back to your code, to find it easier to work with your code, it's advisable that you actually uphold the standard. It's not really a standard, it's just a convention. You could choose to do anything else, but it makes it very difficult to work with your code. But since we want to stick to the convention, we're going to be using .t.so for test files, .s.so for script files, and yeah, so that our code base is easier for review. Okay, so let's get into it. So we now are going to write a test contract. So this was a script contract. And like I said, everything inside Foundry is really just a contract for different purposes. So there are things you can do in a test contract, and there are things you can do in a script contract that you can't do in your standard contract that is going to be deployed on chain, because some of the things that Foundry allows are in contravention to standard Solidity syntax. They're not actual lines of code or commands that could be compiled into bytecode, but they only allow you to interact with your contract in a way that can stress test it and assess some of these vulnerabilities that might arise when your contract is deployed on chain. So I'm going to call this, I'm going to call it on chain is test. So there are certain things that you would have inside your test contract that you get from the test abstract contract. So you'd have to extend the test contract for you to have access to some of those features. And we're going to look at some of them. The very first thing that you have access to when you extend your test contract, your test contract to with a VM test contract, the Foundry test contract rather, is this function setup. So when you remember, when we were deploying contracts with a script, the specific contract function we had to implement for us to be able to deploy the scripts was run. Then for tests, you need to when you extend your test contracts with a Foundry test contract like this, if it inherits the test contract, you have access to a few features, including this function setup, and we're going to see the utility of this function as we move ahead. So if you remember from yesterday, we said that every test scenario that you write must start with a test keyword before we can verify anything else. So I'm going to call this test access control. So inside here, I'm going to write code that tests if a function, rather if the address that is accessing that contract is actually the deployer's address or not, and what happens in cases where it's not. We would typically expect it to revert. Now, what the setup function does is that before you run every test scenario, the setup function runs first. So that means if there are any preliminary things you need to do before you can run your test scenarios, for instance, if you want to deploy a contract instance that you would interact with in your test scenarios, you would do that inside your setup. So if you remember, the keyword we use to deploy smart contracts is new, and our smart contract is called bank. So for us to access it, still we have to import it. So I'll close the script for now, so that we remain with only the two files that we actually need: the test file, the test contract, and the contract itself that we deployed on Sepolia and Anvil. Okay, so we would have to import. First of all, we would have to import the test contract, still from the standard library of Foundry. Forge std. It's called test. They have quite appropriate names, so you don't have to really struggle to find the names. And then I also have to import my very own contract called bank. And where am I going to be importing it from? I'm going to be importing it from, so since I am inside the test folder, I have to get out first into the root, get into the src folder, and then find the contract file, the solidity file that has the contract I want to interact with. That's all. Okay, so that is bank. Now I have to create an instance of bank here. Okay, now if I want to interact with bank, inside the setup function, when I create an instance of bank like that, it's only going to remain exactly inside the setup function. So I need to have access to it beyond the setup function. So I will define a state variable bank here, which is of type bank, and I will call it bank. So that when I deploy the contract, I pass the instance of the contract I've deployed to the state variable I declared, then I can access it inside these other functions. It's just the basic standard solidity as you would, access it anywhere in your other contracts. So now on the bank contracts, which we have deployed now, there are certain sets of functions that I would love to interact with for me to be able to test for access control. So what function has access control among the functions that I have? It is the function deployer withdraw. So what I want to do is now call deployer withdraw with different addresses, one being the address of the deployer, the other being, a random arbitrary address, and see what happens in both scenarios, so that I can test for the functionality or the integrity of the logic that I intended to write when I was writing the deployer withdraw function. So first of all, I need to know what the deployer address was, and I think the deployer address was Anvil 1. I don't think I have it here. This was deployed by approve. So for me to get the address of the deployer of Anvil, I simply want the address, not any of these other things. So I'll simply take this off so I can derive the address. I don't need the balance. Okay, this is is this? No, this is approve. So I want Anvil1, which is the private key, Anvil1. So this is the address that deployed the contract, I believe, if I'm not mistaken. I might be mistaking it for an address, a different address. So I'll simply put it here and call it deployer. Then generate another random address. I would call it imposter. I just want to generate a random address. So I'm just going to create an address, a random address. If you remember from yesterday, we had a function we used to create addresses called make ADDR. And then you pass in a random string, but it will convert it into an address, an actual Solidity address. So I would simply type here maybe. Now you can see the utility of some of these functionalities, because this is not something I would typically be able to do in Solidity, or I might be able to do it, but it might be cumbersome. But now, because Foundry is designed for testing smart contracts, I'm able to do this seamlessly with some of the features that Foundry is embedded with. One of them is this function, make address. So I'll call it, I'll type the word imposter, then it would resolve this to an address, a Solidity address. So now, how would I test if both these functions, what would happen in different scenarios when this function is called? If you remember, there was something we did yesterday. There was a method we called on the VM interface or the VM contract instance called expect revert. If you remember that. So if you remember, what it's used for is just to verify if in instances where we expect the transaction to revert, it actually does revert. So for both these addresses, what instance do you expect that excuse me, the transaction would revert? Of course, it's when the imposter makes a call to the contract, that the contract function that we're going to put under expect revert. So what happens with expect revert is everything you put directly under it should revert, and that's when the test is successful. If it doesn't revert, then the test fails, because when you expected the transaction to revert, it did not revert. So for expect revert, everything you put below it should revert automatically. That's when your test is successful. Like, you expected it to revert and then it did revert. So I have an instance of the contract that I want to call bank. Then what method am I going to be calling on this contract? Deployer withdraw. Was that the way I typed it, or was that was the event? Deployer withdraw, the function doesn't have a hyphen, rather underscore below it, in between it. So this is the function, deployer withdraw. Now when I call this function, I have two addresses. So for me to specify which address is going to be making this call, I pass that address inside expect revert as the address that is going to be calling the functions. So expect revert, now I want to pass imposter in, but deployer withdraw requires one argument before you call it. It requires the amount that you're going to withdraw. So for instance, if I wanted to withdraw where is it? It's right here. If I wanted to withdraw just a simple amount of ETH, maybe okay, does it work? Would it revert? Would it actually revert? There's only one way to find out. We need to run the test. So we're going to run the test. And the keyword for running a test is forge test. So if I run forge test, it would run all the test scenarios in the test contracts. But they didn't specify visibility for this function. Could be public. So when it compiles, I expect it to revert. and it says unused local variable deployer run one test, and it failed. Okay, why did it fail? We can find out why. Encountered a total of 1 failing test. So when I called expect revert with imposter as the address, it did not revert, in the sense that just a moment, imposter. Okay, did I enter that correctly? So it is supposed to revert. Sweet result. 0 passed, 1 failed. So I can find out why it failed by getting a verbose result. Perhaps I could know where the error was. So when the execution, when this test scenario was executing, vm.address did generate an address imposter. You could see that here. Then expect revert, custom error, that it returned successfully. Now when I called bank.deployer withdraw, it reverted at 2 points. It reverted at this point where it says unauthorized. So the user is not allowed to execute this transaction, although it's supposed to pass. Custom error. Find out what this is. Expect revert is supposed to actually return, to actually work, unless there's something I didn't do correctly. Let me first remove that address and see what happens. Let's execute it. Deployer withdraw. It did not work still. So how about if we passed in a deployer? See what happens. Does it run successfully? This address is also unauthorized. So who deployed the contract? What address did we use to deploy the contract? I thought it was this one. Deployer withdraw. Okay, I think I know the issue as well. All these addresses don't have any funds. So I'm generating these addresses, but I haven't funded them. So that's why, I think that's why it's not working. So I'm trying to send value. Actually, I'm not sending any value. That's the value I want to withdraw. Sorry. Oh, I'm just withdrawing. So the contract doesn't have funds, but they should be able to make the call. They're not actually sending value. They're simply withdrawing value. If address this is better than that. Failure. Okay. So I know the issue was I did not declare a constructor. I forgot to declare a constructor and assign msg.sender a value. So it resolved to address 0. So the address 0 is kind of like the value of the deployer, although it's not the address that actually deployed, but the original value of an address is always address 0, and I did not change it. So that's why it's raising an error, I believe. I could verify this by using address 0 to make the call and see what happens. Expect revert. So this should execute unless there's another error. Deployer withdraw, still unauthorized. there's something I need to figure out, but that's okay. Let's do the correct thing first. Let's add a constructor to the contract so that we're able to interact with the contracts in the correct way. So we'll simply add a constructor here. And in the constructor, the msg.send at the point of deployment of the constructor, or of the function rather, of the contract rather, should be assigned to the state variable deployer. Okay, now we have the correct deployer. And actually, when I come back to my setup here, okay, I had to set up a specific address to make the deployment in the setup function. That's where I would use vm.prank. Now what happens with vm.prank is that it uses the address that you're going to put inside prank to make the next call or the next transaction at the bottom. Okay, so what I'm going to do here is just assign this deployer. Actually, I should make this a state variable, so that then I could use it below in other things. Simply say deployer here. So that will be the address that does the deployment, the actual deployment. Okay. Moving forward. So we have an address of the imposter, then we have the address of the deployer. Address 0 still wasn't working, but expect revert is supposed to raise an error every time something passes when it's supposed to fail. Okay, so we tested it and it wasn't working. And let me get back to it. Expect revert. Right, sorry about that. It's just an internet issue. Okay, it was just an internet issue, but hopefully we are good now. Okay, I think we can resume now. We're back online. Okay. All right. So what we were doing, let me do it this way. So the deployer is that address, and then down here, what I'll be doing instead of using expect revert in that format, I'm going to start a prank that simply specifies an address that should be used to make the next calls until you specify to stop the prank. You remember when we did start broadcast and stop broadcast? So the same thing happens with start and stop prank. It would use that address to make the next calls until you stop the prank, including the one where you would use the deployer withdraw address, rather call the deployer withdraw function. Okay. So I want to test this now and see. It failed because I forgot to put this. So this fails. Says I'm unauthorized. VM.start prank, stop prank, unauthorized. And it's being called in the same context as same context. Okay. It says I'm unauthorized, so let me use the deployer now and see what happens. The deployer address. Someone asking a question. Okay. Alright, so now I changed to the deployer address. Imposter, unused local variable. So it passes. The only issue now comes to the wallet balances. The contract does not have any balances yet. So now, originally what I would do maybe is fund it. I'm going to give it a value of a certain amount of tokens so that it has some funds as the wallet that we're going to call later on. So I could do that in setup, or I could do that still in my test scenario. So the balance is low. That's why I can't withdraw, because there's a require statement inside that function that checks if the balance on the wallet, rather on the contract, is allows for the amount you requested to withdraw. Okay, so VM. So now here is where I would use VM.deal to fund this wallet, this account rather, smart contract in this case. VM.deal. So in this case, I would send funds to it. First convert it to an address, and then specify a certain amount of ETH that I will send to it. Maybe 30 ETH. Okay. So it didn't have a balance, that's why it failed. Let's see what happens now that I've funded it. Next call did not revert as expected. But when you look at this transaction, it was successful to the point of the emission of the event that we expected to be emitted. About expect revert, there are a little bit more details, but I am going to get back to it. For now, let me write another test scenario so that we can test for other things. For instance, test. What are we going to test for? What other thing can we test for? So we've verified that the deployer address is the address that did make the deployment. Maybe we could verify what the deployer address is. We could test for deployer address. What the deployer address is, if it's actually the address we expect to be the deployer. So here I'll simply make an assertion, and let me see how I want to test it. Okay, this is what I'm going to do. I'm going to make an assertion, assert if the deployer address I have here is the same as the one that the function, rather that state variable has. Where is that state variable stored? It's stored in bank. So I'm going to call the deployer address immutable deployer. I don't think I can actually call it because it's not public, but I can make it public still from right here. Since I'm not deploying, I'm just testing, and I call deployer the getter function that is defined for it. So now I'm going to call this specific test scenario deployer address to see if it actually passes. And that's the keyword you use for. Let me first remove all this so that we can see it. Forge test, match test. So the test is called deployer address. And let's see if it actually passes. If the deployer address we think is the deployer address is actually the deployer address. So the compilation failed for a reason I'm about to find out. Test deployer address. Simply making an assertion if the deployer we have in the on-chain test contract is the one that the deployer address has. The deployer state variable has immutable. Perhaps what I will do now is just declare a getter function for it since it's immutable. Deployer public view returns. It returns an address. I just want to really return that address and see it. Deployer. I'll just define it like this with a Then in the test scenario, I simply call that specific function because it's public. Let's see what it displays. So I forgot that. I think it's because of working a lot with JS lately. I keep forgetting semicolons. Why is this failing? Function assert. Test scenario. I'm simply making an assertion. If this is equal to that, rather if this is equal to that, so I expect it to pass. Let me see the error. It says identifier already declared. Okay, let me just change the name of deployer. I'll call it deployer func and simply call that function here to see if the test scenario passes. So I was just replicating a name and it does pass. You can see one passed. If I want to see the details, so what that verifies to us is that the deployer address we think is actually the deployer is really the deployer. So we won't have any issues later on, and that is the deployer address 2266. Is it the one that I had? Yes, it's the one that I had. So I could also test as the other specific scenario, the first one we had that had expect revert. Start prank, stop prank. This should pass. Deployer withdraw. So this specific function had a number of tests. One of them was to test for if the amount is exactly what it's supposed to be, but the other test is also in the modifier, where we're checking if the function that is, rather the caller of the contract is exactly what the deployer is. And if you're not, it will tell you you're unauthorized. So coming back to it, I want to test it separately as well. It's called test access control. Test access control. So it was successful. Next call did not revert as expected. At what level did this fail? Okay, this did not revert because of course we were using the deployer, but if we change this to the imposter, this would fail at the very start, and that means our transaction will be successful, rather our test. And this, so it passes, the test actually passes. When you see down here, the test passed, but because it reverted, in the sense that it did exactly what we expected it to do, to revert. It shows the message here that it did revert, but the test is successful, and it reverted just as we expected it to revert. All right, so those are some of the things we could do with tests. Now I'm thinking of something that we could look at. Another thing that we could look at in detail that might give us a little bit more context about Solidity in relationship with Foundry. So there's a number of other things. Some of them are a little bit advanced. I won't get into them now. But I think let's take a look at gas optimization at the level of storage. Perhaps that would be something we can look at. It might take us about an hour, and will be a very good lesson, I think, for us to understand how gas can actually be optimized and why it's important for us to work with functions a certain way and state variables a certain way. Maybe to start with, but I hope there are no questions so far about some of the tests that we've been executing. Any questions, any feedback, any additions? I would appreciate it, please. Okay. All right. So I'll just move ahead then. Okay, so so far we've looked at fundamentals of testing and fundamentals of scripting. So there are certain things we could do, things like integration tests, things like fork tests. But yeah, let's leave testing at that for now. We shall look at it more practically as we go. Now, I want us to look at something that might be a little bit. Anyway, let me just do it. So I'm just going to test something about storage regarding this specific contract that I deployed, and how all the state variables and variables are arranged in the EVM slot, in the EVM slots. So maybe before I get into that, let me look at Notepad and explain what EVM slots are. So every machine has a mechanism with how it addresses its memory and storage. So some computers address their memories and storage at the levels of bytes. That means every single byte is a single storage unit. Some others address their memory in different storage capacities, but the EVM addresses its memory in 32 bytes capacities. So that means every single unit of 32 bytes is recognized as a slot. So when you think about it, look at it like a shelf of drawers. Let me use paint. Hope this would be easier for us to observe. So think about EVM memory, storage particularly, as just squares that are contiguous sets of squares. Of course, they're the same size. My hand is just funny at drawing. So for instance, if we had, if this was EVM storage, each of these boxes is 32 bytes, and it stores values that would cover that space. 32 bytes, 32 bytes, 32 bytes. So every time you store something into memory, or rather into storage, it is stored into slots of 32 bytes, slots of 32 bytes, slots of 32 bytes. That's how EVM storage works. And unfortunately, not all state variables, depending on the type, can cover that space entirely. So sometimes you might find that you have an address is 20 bytes, so it would cover up 20 bytes of this space, and then the remaining 12 bytes are not covered. But then, if you had 12 bytes, then you can store something that can be stored in 12 bytes, probably a uint 8. That's exactly 8 bits, 8 bytes, rather 8 bits, so that's 1 byte exactly. So you would store, that would cover maybe 21 bytes, then there will be 11 bytes that are left. And then if you had a U into 56, it cannot fit in the remaining space that is left, so it has to be shifted into another slot. Because a U into 56 covers the entire 32 bytes, no matter what digit you're storing in the state variable, it covers the entire 32 bytes slot. If it's a uint 8, it would cover only 1 byte of the 32 byte slot. So for me to cover an entire range of 32 bytes, with uint 8, I would have to store exactly 32 values for me to cover that entire space. If I was supposed to store those exact same values, if there were U into 56s, I would have to have exactly 32 slots to store each of those values. And we're going to see why it's important to actually always estimate the range of the value that you're going to store, and then determine the specific type that will be the most appropriate, so that we don't waste gas. Because every time you're writing to a new slot, you spend more gas than if you stored all your variables and packed them into a single slot. So if I had maybe 3 state variables that could be stored in this single slot, it would cost me much less gas than if I had to spread all those 3 slots across, spread all those 3 variables across 3 slots. For instance, if I had values that could fit in U into 8, and then I choose to use U into 56s, 2, 5, 6. If I had 3 values of U into 8 and I had 3 values of U into 56, even if they were really storing the same digits, these values of U into 8 would use exactly 3 bytes. You get it? Which is exactly 1 slot, which is not even full. So we would have 29 bytes unused in that specific slot. But if we store those same digits inside U into 56s, we would need 3 slots, which is 32 times 3, and that is, what is that? 98 bytes? Are they 98? 32, 32, 96, 3, 6, 9, 96 bytes. 96 bytes. That's a very large number of storage, unnecessarily. Because when you look at the disparity between these two amounts of storage is so high, and yet if they were already storing the same values, this would definitely cost me more gas than that. That's precisely it. And we're going to look at how these are actually stored by just looking at state variables and how to work with them. So typically you can access values that are stored in storage using the keyword vmload, and you can access them. First of all, you start with the address that you want to, whose storage you want to access. So the first parameter would be the address, and then the slot number in bytes 32. Okay, so that's just how we use VM load. Now we're going to see how this comes in handy when we're working with smart contracts at much deeper levels. Even when we start to get into things like smart contracts auditing and evaluating how these slots could potentially be manipulated and then modify data on a smart contract if someone probably gets some access to that low level state. VM load, that's how I would access any values stored in state. But this is what happens. How do values actually get stored and how do they get arranged in your storage? So the very first thing you need to pay attention to is how you arrange your state variables when you're declaring them. So everything that is stored inside state variables is stored from the leftmost slot 0, onwards to infinity, depending on how many state variables you're going to be storing. Of course, depending on how much gas you can accommodate. So if I had 3 state variables declared from the top to bottom and they can fit in 32 bytes, they would all be fitted in this 32 byte slot. If I had more state variables, they are arranged in the order of their declaration. So if these can fit here, they would be put here. If this can cover 3/4 of this space, it would be put here. If this other state variable can also fit in the remaining space, because they are stored from right to left, that might be a little bit counterintuitive, but the very first state variable is stored at the lowermost bytes of the 32 byte storage. So for instance, if we had the 32 byte storage ranging from 0 here up to somewhere there, if I have a 20 bytes address, it would be stored first in that range, and then the rest of this space will be waiting for another state variable if it can fit there. If it can't fit, the compiler would the EVM would shift it onto the next slot. But if it fits, of course, it would be put into the rest of this space. And this is where it comes in important. For instance, if I was defining state variables, then I define a uint 8, and after that I define a uint 256. uint 256. What is going to happen is that the uint 8 will be stored in slot 0, but the rest of the space that remains, which is exactly 31 bits, cannot accommodate a uint 256. So the uint 256 would have to be shifted into the next 32 byte slot, which means the rest of the 31 bytes from the very first slot 0, have been left unused. Because the next variable cannot fit in that space, it has to be shifted into the next slot. So otherwise, if I had defined the uint 256 first, it would cover up the entire 32 byte space, and then the uint 8 would be shifted to the next slot. Then now we have the rest of the other space for any other state variables that could be declared. So what is typically recommended? Let me give an example here, perhaps. If I had a uint 8 with the size that they would cover, a uint 8 and this is the arrangement I'm defining them. Perhaps I'm giving them names, maybe state variable 1, and this is state variable 2. uint would definitely be a uint 256, and this is an address, state variable 3. So this typically covers 1 byte. This covers 32 bytes. This covers 20 bytes. This is an address. An address is 20 bytes. So when I look at the configuration of these declarations, this is what would typically happen. This would go to slot 0 and use up only 1 byte. And then the balance we're left with is exactly 31 bytes. But you know what? 31 bytes cannot accommodate a uint 256. So what is going to happen? It's going to be shifted into slot 1, and it's going to cover up the entire 32 bytes. Okay. Then what is left? We are left with 0 bytes in the second slot. Then going to the third slot, because of course now there's no more space in the second slot, slot 1. So we're going into slot 3, slot 2 rather. Slot 2, an address would cover up the last 20 bytes. Then would be left with how many bytes? Would be left with how many bytes? That would be 20 minus 32, that's 12 bytes. So when you look at this configuration, 31 bytes are getting wasted on the first slot, and 12 bytes are getting wasted on the third slot. And when you're writing smart contracts, these are some of the things that we take for granted, and that's why sometimes when you reach to deploy a smart contract, because it requires a lot of storage space on the EVM, it ends up failing to compile. But it's something that is very subtle and difficult to figure out. But let me give you a solution that could be more gas efficient. What if instead of us defining and arranging our state variables like this, we started with the address itself. Let me say we have the address here. So we started with the address, which covers 20 bytes, and we're left with 12 bytes on slot 0 now. And then we went on to storing the byte, the uint8, which is of course a byte. This will still be slot 0 because there were 12 bytes that were left, and we're going to use one of the bytes that has left from the 12 to store the uint8. So now I'm packing the state variables. Instead of me spreading them across different state slots, I'm going to store them in a single slot. This will be left with 11 bytes. And then, so now when you notice we're still on slot 0. So now instead of us using exactly 3 slots, we are going to use only 2 slots. And 32 bytes. So this would be now slot 1, which would be the second slot, storing the uint 256 and using up all the 32 bits. When you look at this, originally we had used 3 slots, and every time you write into a slot, you spend more gas than you would if you packed all your state variables as much as you can in a single slot on the EVM. And the 32 bytes uint256 was stored on slot 1. So the configuration with which you declare your smart contract state variables matters a lot in determining how much gas you consume when you're deploying your smart contracts, because of the space that is designated to those state variables. So to think about it, if this state variable that is called a uint256 was going to store values that could be relatively smaller and could fit into a smaller uint type, maybe a uint16, I could just end up storing them there as well. How much space would this cost? Instead of now me shifting into slot 1, I would now store all 3 state variables in slot 0 because the amount of space they require can actually fit in 1 slot. So let's look at this practically and see how you can actually access them and observe where they are actually stored. And these are some of the things that smart contract auditors actually do to evaluate things like gas optimization, especially for very large protocols and protocols that have long lines of inheritance. So what typically happens, let me also demonstrate that and why it's important, especially when you are working with contracts that have a lot of inheritance. If a contract has inheritance and maybe is inheriting about 3 other contracts or 4 contracts or 5 contracts that potentially have their own state variables already declared, all that space is going to be consumed by the state variable, by the contract that is actually calling those contracts. All those state variables are going to be stored in the contract that you're using, that is implementing all those other contracts. So it's important to know how to configure your state variables in a way that is gas efficient. But like you see, it's a very subtle concept. It's not something that you would see as an error or something. Oh my God, I'm looking for a pencil. Okay, for instance, if we had this inheritance tree, and this is contract 1, then contract 2, and we are interacting with contract 3. So contract 3 inherits contract 2, and also inherits contract 1. So if this has 3 state variables and this has 2 state variables, all these 5 state variables are going to be declared. When you start deploying contract 3, all these state variables are going to be declared in contract 3. So if it has 5 more, which by the way, these are very small numbers, depending on how large the protocol is. So you have now a total of about of exactly 8 state variables. The way they are configured in contract 1 is exactly the same way they are going to be carried down. So even the second smart contract is going to have its state variables carried down in the same configuration. And as well, now you have this. So you'd have the storage layout of contract 3 like this. The contract 1 state variables would come first. These would they'll be the ones that are recorded first in slot 0. Then the state variables of the contract that you're interacting with are recorded last in that hierarchy. So if you're working with things like mappings can be very large, and they're increasingly extensible. If you do not configure it in a gas efficient way, at some point your protocol becomes expensive, even to use for end users that are just coming to interact with it, because they're the ones that are supposed to sign the transactions, which will eventually store values on the state variables of those data structures. So if you've seen, sometimes you're making a swap or you're trying to interact with a certain protocol, like it is more expensive than the other. Sometimes it's not just in the logic of the code, but in the way the state variables are arranged and stored. So let me look at something very practical in a very short time. Hopefully we finish in time. I think we've done a bit of testing and it was successful. So I'm going to declare 3 variables here and see how they are configured in storage. So I'm interacting with a bank contract. And when I look at the bank contract, how is it configured? So like I said, this one goes directly into bytecode. So this is one of the ways you can optimize for gas. Some of the variables, actually constants especially, you don't have to store them in the slots. Just take them directly into bytecode by making them constant or immutable. So at slot 0, we would expect to see safe balance. Safe balance. I don't think we actually increase it anywhere. So it's always going to be at 0 until we call the deposit function and send some funds to it. So I'm going to call safe balance here and increment it by the value that has been passed in, that has been sent in as msg.value. So I expect that the funds that I'm going to send to the contract at a certain point are going to be the balance of safe balance. Then I can access this value through vmload, hopefully. So when I come to my test contract, I have the smart contract here, and I'm going to run the test scenario in storage here. So now I need to call the bank contract and deposit. Deposit, I think that's the method. But deposit doesn't take in any parameters. It simply uses vm.value. And it's external, it's payable. So I have to run a prank, for instance, or maybe I need to first fund the wallet or the account that is going to make this call. So I want to fund the deployer. I'm just going to fund deployer with some funds and allow them to make this call. So vm.deal vm.deal. The address that I'm going to fund is called deployer, and I'm giving it 10 ETH. So now the deployer has some funds, so I want him to be the one that makes this call. vm.prank. vm.prank, who is going to make the call? The deployer. And when they make the call, I want them to send a value along with this call, a value of maybe 3 ether, so that now I can see that the value of the state variable which I want to see, which is safe balance, is visible to me. vm.load. This I'll do it later. But maybe I could even check if deployer actually has some balance before it does the prank using console.log. If you remember that from yesterday, it's just this you can't do in Solidity, standard Solidity. It's only accessible through Foundry because it allows you to check some things within your test scenarios before you can maybe to kind of troubleshoot, but also to see the progress of your work. So I want to see the balance of deployer.balance to see if it actually has some funds. So I'm simply going to call this method and then first comment this out to just verify if it actually has some balance, if it actually got the 10 ether that I gave the address. I want to call this balance and then make the call here, forge test, but I want to run a specific test called storage. This is a test scenario I want to run, but then I want for it to be verbose because that's the only way I can be able to contain safety. That's the only way I can be able to see what has been printed. No visibility specifier for storage. I want this to be public. Keep forgetting these things, I think, because I'm running first. But let me see what this is. Console.log isn't declared, that's true. So I have to import it from the standard library as well. Okay. I'm trying to run fast through it so we could do something practical. And it says no test found in project forge looks for functions that start with test. Now you can see that it actually caught up with me. Every test scenario has to start with test before any other keyword that defines the test scenario. So that's the error. And it compiles and then shows me that this account actually does have the 10 ETH that I gave it. If it was 1 ETH, this would be 1E18, but it's 10 ETH, so it's 1E19. So it actually has the balance, and it can make the call. Okay, let's see if it can actually make the call, vm.prank, and it makes the call depositing 3 ether to that specific contract. Okay. Compiled successfully. So it worked. It did deposit the value, you can see. Deposit was successful by that address, and those are the funds that it sent. Alright, so now what are we going to do? We are going to verify if the value stored in storage slot 0 is actually the balance as we expect, because it's the state variable that was declared first, safe balance. And we're going to do VM load, just a simple basic thing. VM load on the contract that we called, the contract instance that we called, because that's the contract whose balance we want to check now. The contract is called bank. Then the byte 32 equivalent of the slot, it's just slot 0. So you go into 56. This would be a 0. So the thing is, you can't directly convert a number to a byte 32. You would have to get the byte 32 equivalent in numerical format, which is 0 into 56, before you get the byte 32 equivalent. So I expect it to load for me a byte 32 result, because it returns them in the format of the storage slot, like how many values are stored in that specific slot. If there are 5, it would return the byte 32 equivalent. Then you can decode it perhaps yourself. So I would call it a result and then print it perhaps. Print it down here. What is very interesting is, anyway, let's first do this. Result. So for bytes 32, you can't put them in result, rather in a console log, it has a specific print statement of its own. Console log bytes 32. We'll import that as well. Anyway, that's it. So I'll put it here and say result. So I expect to see a bytes 32 value that represents the 3 ETH that I deposited. So you can see our test scenario is being complete. We haven't deployed the smart contract. We're simply running tests, but we can check almost every single thing about this smart contract in just a test scenario. And so this was successful. The test ran successfully, and this is the value it returned, bytes 32. We can verify if this is actually 3 ETH. Maybe if we convert it to deck and I say cast to deck bytes 32, it actually results into 3 ETH. You can see that. To verify that, of course, we could check this on the we could check this on, do we have, I think I removed it, just a way calculator to see if this is actually 3 ETH. So that's typically how you would use test scenarios to do a number of things. So what I'm doing now is just focusing on storage. And I don't know if we'll have time. There's something I want to demonstrate that might make a little bit more sense in how smart contracts auditing would be critical if you do it at this level. And if we maybe have some time tomorrow, we would also get into assembly and see how this is very powerful and how you could do it even more deeply. So this is 3 ETH, as you can see. So that's the value that is stored in slot 0. But it's a U into 56, so it can't share the slot with anything else. But I'm going to show you something and how these smart contract state variables are actually packed together. So now 32 bytes, that would take the standard price of gas to write to it, to write to that specific slot. But now when I look at the second state variables that I declared, okay, the second is a mapping. Let me put the mapping down so that I can allow myself to use to use slot 1 for something else. Maybe if I had the address and I had a uint 16. Oh, this is an array. Say that is also an array. Arrays and mappings have a very specific standard with how they are stored. I don't know if we'll look at it today, but I just want to demonstrate now how we can have two values stored in the same slot that would otherwise be split across different slots if they were uint 56s. If I had a uint 16, that was of course public, and I call it just a random value. I'm not exactly going to even use it in the smart contract. I'm just trying to demonstrate a concept, and maybe it's stored a value 200. Uint 16, I believe, can store 200. And I had another value, maybe a uint 128. That was also public and stored a random value as well. Random val 100. I want to notice something that, okay, uint 16, uint 128. Let me first make them both uint 16s, and we look at this. So now instead of me looking at slot 0, I want to see what is stored in slot 1 of that contract bank. So the result I expect should have both values stored. We can verify that. Okay. So I run the same test scenario, compiles, and then returns the result for me. And where's the result? This is the result. You can see it's almost like, I don't even know how to explain it, but it's almost like the rest of the space is left free. This is all space that could store another value when you see that. But for the uint 56 stored in slot 0, it covers all the 32 bytes and leaves you with no space for anything else. even when the space could actually accommodate a different value, another value, they're by default stored into a space of 32 bytes, a range of 32 bytes. And basically, that's how storage optimization could be achieved, just by simply rearranging your smart contract state variables. There's a lot of power that could come along with that, allowing you to interact with your smart contracts in a way that is more gas efficient and in a way that is, simply gas efficient. I don't know if we should go ahead and look at mappings and arrays or any other thing in that regard, or we could close it here. Otherwise, it's a little bit more detail, but because of time, might not be able to cover everything. Any recommendations? Should we proceed into anything deeper, or we could close it here? Okay, no response simply suggests we should close, I believe, I presume. What does that mean? Should we move on? Should we close? That's enough. Okay. All right, yeah, hopefully we'll resume tomorrow. So tomorrow I want us to look at fork tests and get a little bit deeper into testing with live smart contracts that are deployed. You could practically test with a protocol. Like if you have Uniswap deployed on Sepolia, there are certain things you can test within your Foundry contract with the functions and contracts that you are working on yourself against the activity on Uniswap. Either you want to track certain events or you want to track certain state changes, and then your contract reacts in a certain way. All those things are possible with Foundry, and you can test them before you deploy your contracts, including deeper gas optimization, where we can see the actual gas that it would take for us to deploy certain contracts or do certain calls. It's very fascinating, the things that Foundry can do, but hopefully it's something that is being helpful, the sessions we're having. All right, we can resume from here tomorrow perhaps. Have a wonderful evening.